Okay, so our next speaker is Michael Jardim from University of Campinas, and he will talk about Instanton sheaves, the next frontier. So please, Michael, you can start.
Good morning or good afternoon, everyone. First, let me thank Valeriano and Hugo to give me the opportunity to participate in this meeting and give my my thanks and my happy birthday to Claudio.
Thank you.
I'm 1 week into the future, so I apologize for the wrong date in my initial slide. So I had 2 joint papers with Claudio. Both ended up being published in 2004 on conference proceedings. So first was a conference, so the first paper is a conference that was in 2002 in Cookeville, Tennessee, right? So a special session organized by Hugo, and but we met before that, right? So I think we met a year, maybe 2000 or 2001 in UPenn.
UPenn, you're right.
And that's when we started discussing num-transform, and these 2 papers are our contribution to some variations upon the num-transform, right?
Right.
And what I'm hoping to talk about today is not so much about the num-transform. Hugo already gave us a hint, talking about the hyperkähler num-transform in his presentation. But actually, I want to offer a little bit of a history of mathematics and physics, talking about instantons and actually Instanton sheaves. So Instanton sheaves in algebraic geometry and how they came to be. Some almost 50 years ago, right? So at least some 45 years ago. And everything starts with this so-called twister diagram. Let me try to explain what it is. So if you start with the 4-sphere, S4, you can pick a point, call it a point at infinity, and then this 4-dimensional sphere can be regarded as the Euclidean space, is a conformal compactification of the Euclidean R4, 1-point compactification of the Euclidean R4. And then it turns out by Uhlenbeck's theorems that instantons on anti-self-dual connections, a bundle with anti-self-dual connection on R4 is the same as an instanton on S4. On S4, we have this so-called twister map from CP3, whose fibers are copies of CP1s, right? So the fibers called the twister lines. These fibers, they parameterize the possible choices of complex structures on a tangent space to a point in S4 or R4. So S4 itself is not a complex manifold, but it's what is called a quaternionic Kähler manifold. And on each tangent space, you can choose a complex structure. And this choice of complex structure is what gives the lines of this so-called twister map. And above this point at infinity of S4, there is a line called a line at infinity on CP3. And if you pick up any CP2 here, any CP2 containing this line at infinity, and there is a P1 worth of these choices, right? So there's a whole pencil of hyperplanes containing this line at infinity. This amounts to choosing a complex structure on the R4, right? So on R4, you can make a choice of a complex structure, identifying this R4 with CP2. And if you compactify this CP2 by adding a line at infinity, you get this CP2 inside L2 containing the same line at infinity there in CP3. Right, so this is a little square that was worked out by Penrose probably in the 70s, when he started considering twistor theory. And that played a very important role in the development of gauge theory, because that was actually the first point in which gauge theory met algebraic geometry, due to the work of Atiyah, Drinfeld, Hitchen, and Manin in 1978, if I'm not, well, that's the date of the published paper. So in this paper, what these four authors, Atiyah, Drinfeld, Hitchen, and Manin, actually, it was a work done between Atiyah and Hitchen in Oxford, and Drinfeld and Manin in Moscow, and via some exchange of letters, Hitchen and Drinfeld realized that they were working on the same thing and decided to make a joint paper, which was really something very unusual, right? Back in 1978, to have a joint paper between British mathematicians and Russian mathematicians. But anyway, so the important discovery made by these four authors is that if you take an anti-self-dual connection on S4, or anti-self-dual connection, an instanton on R4, or an instanton on an S4 framed at this point at infinity, then you can pull back this bundle of connection to the twistor space, to CP3. And it turns out that the instanton condition, the fact that the self-dual part of the curvature of the connection A vanishes, is exactly what you need for the 1-1 part of the pulled back connection to vanish on CP3. Which means that the pullback connection induces a holomorphic structure on the pullback bundle. And this holomorphic bundle, it's not just any holomorphic bundle. Well, for starters, it has to be trivial on all the twistor lines of CP3. Particularly, it has to be framed at the line at infinity, the same notion of framing that Ugo just spoke about in his presentation. It comes with a reality condition that will not be important for this talk, so just ignore it. And most importantly, it comes with this vanishing condition, right? So the some H1 cohomology of this pullback bundle equipped with a holomorphic structure has to vanish. And this vanishing of this cohomology is related to the vanishing of a differential operator coupled to the instanton connection. So it's really a point, and this was also something that this is so-called the Penrose transform, if I am not mistaken. So this was already something that was realized by Penrose in late 60s, early 70s. This link between sheaf cohomology and kernel of certain differential operators. And then it was used by Atiyah, Drinfeld, Hitchen, and Manin to show that the bundles that you get on CP3 satisfy this very special vanishing condition. But then, given this bundle on CP3, you can also restrict this bundle to CP2, and you get another holomorphic bundle on CP2. Well, we get another holomorphic bundle, this time on CP2. And this bundle on CP2 will be framed at this line at infinity. And these are exactly the holomorphic bundles on CP2 coming from instantons that Ugo mentioned in his talk. Right? So there is a, in all this, various, these various objects can be summarized in this diagram. So at the base, at the bottom of the diagram, you have the instantons, the anti-self-dual connections on the four-dimensional spheres, framed at the line at infinity. On top, you have two types of holomorphic bundles. One are the holomorphic bundles on CP3 that come, they are called the instanton bundles on CP3. So the bundles on CP3 that come from an instanton on S4, which means the bundles on CP3 that satisfy this cohomological vanishing here. And these are called the Instanton bundles on CP3, equipped with a reality condition, and also holomorphic bundles on CP2 framed at this line at infinity. In the middle of this diagram, there is are these so-called ADHM equations that Hugo already mentioned as well. And all these correspondences can be made via, right? So passing through this middle square related to the ADHM equations. And the various arrows that I drew here were worked out by various people. So the link between the Instanton bundles on CP3 and Instanton on S4 is the so-called Ward correspondence that is detailed in a paper by Atiyah and Ward from 78, I think, 77 perhaps. Then there is the ADHM construction relating ADHM equations and the Instanton bundles on CP3 that was worked out by Atiyah, Dreamfield, Hitchen, and Manning. Donaldson worked out was the first to work out the relation between the ADHM equations in the holomorphic bundles on CP2. In a paper, very short paper called Instantons and GIT, which Donaldson calls unashamedly computational, which I think is quite peculiar. So this arrow here, this link between the Instanton on S4 and the holomorphic bundles on CP2 can be done directly. And this is a bit of analysis, right? So you get an Instanton connection here on R4 gives you a holomorphic bundle on C2, and this holomorphic bundle can be compactified to a holomorphic bundle on CP2. So this is this arrow here that was worked out by a student of Donaldson. And then there is this arrow here on the top, the arrow from the right to left, from the bundles on CP2 to the bundles on, sorry, from bundles on CP2 to bundles on CP3 is just restriction. But then actually, I do not know how to make the arrow from CP2 to CP3 directly, right? So without passing through the ADHM equations, right? So I don't know how to, given a bundle on CP2, what are conditions for this bundle to extend to a bundle on CP3? I don't know how to do that directly. And I don't know if this is in the literature somewhere. Yeah, so this is more or less the state of things around 1982, more or less, or 1984, around the date when Donaldson wrote his paper, and shortly after this student also had a PhD thesis on this correspondence here. So I mentioned here the ADHM data and the linear monads. Also, again, something that Hugo already mentioned in his presentation. So the ADHM data is made up of two vector spaces that I called V and W, two endomorphisms of V, two operators on V, and maps from V to W and W to V. These are the data that you can encode in the quiver that Hugo wrote in his talk. These are the two ADHM equations. There is the complex ADHM equation, which is the first one, and then the real ADHM equation. That's not so relevant. But what happens is that out of this, these matrices, A, B, I, and J, you can concoct some some maps of some bundle maps, alpha and beta, that give you a monad, right? So this here on the bottom of the slide is a linear monad. Linear because all the maps, these alpha and beta, are matrices of homogeneous polynomials of degree 1, right? So that's why this is a linear monad, so-called a linear monad. And this is the technical, the idea behind these constructions from the ADHM equations to bundles on CP2 and to bundles on CP3, right? So out of the matrices, you make a monad, and then you look at the cohomology of the monad, which means the kernel of beta quotient out by the image of alpha, right? So beta is a surjective. If you pick the right matrices here, beta is going to be surjective, alpha is injective, and the cohomology, the only non-trivial cohomology of this complex, will be one of these Instanton sheaves, either on CP2 or on CP3. So this brings us to the beginning of the 80s. This whole picture that I mentioned for S4 can be generalized for higher dimensions as well. Remember, S4 is HP1, right? So it's the case, the diagram that I wrote before is this left, the square on the left of this diagram here, for the case k equals 1, right? So H4, the fourth sphere coincides with the first quaternionic projective space. So the twistor space of the quaternionic projective space in dimension k will be this odd dimensional complex projective space. And again, you have a version of the Atiyah-Ward correspondence here that provides a correspondence between the quaternionic instantons on HPK, right? So again, something that Ugo mentioned in his presentation. So the quaternionic Kähler instantons on the quaternionic projective space and holomorphic bundles on this odd dimensional projective space, satisfying some vanishing of cohomologies, right? So satisfying some cohomological conditions here, vanishing of H1, vanishing of all these HPs here, doesn't matter so much what they are. But you inside this this twistor map, you can look at the divisor at infinity, right? So the hyperplane, the quaternionic hyperplane at infinity. That's what this HP k minus 1 here represents. It represents the hyperplane at infinity of this HPK. Over this HPK, you have this codimension 2 plane inside the odd dimensional complex projective space. And now again, you have a pencil of even dimensional complex projective spaces, CP2Ks, that contain this CP2K minus 1, right? And then so it's really, this is just a hyperplane, an even dimensional hyperplane inside this odd dimensional complex projective space containing this codimension 2 bit inside the complex projective space. Okay. And it turns out that as an open subset inside this CP2K, you have this C2K, which is isomorphic to HK, which is precisely the complement of this HPK minus 1 here, this quaternionic projective space at infinity. And this map phi here that you get is some sort of a quaternionic blow-up. For lack of a better name, I call this phi here the blow-up of HPK along this hyperplane at infinity. The moral here of this slide is to tell you that coming from these quaternionic instantons on quaternionic projective spaces, you get a family of holomorphic bundles on odd dimensional projective spaces, which are defined via these cohomological vanishing conditions and their restrictions, right? So the restrictions of these bundles coming from instantons on quaternionic projective spaces to CP2 will also be some sort of vector bundle now on these even dimensional projective spaces, also satisfying some sort of cohomological vanishing conditions. These observations led me to consider this definition of the Instanton sheaves on projective spaces. So this is a paper from 2006 in which I introduced this notion of an Instanton sheaf. So sort of generalizing this notion of Instanton bundles to consider not only locally free sheaves, right? Because now these Instanton sheaves are allowed to, in principle, allowed to be non-locally free, but also look at sheaves of arbitrary rank on CP, on projective spaces of any dimension. And these Instanton sheaves, they are defined via these vanishing conditions. Right, so an Instanton sheaf on CPN will be a torsion-free sheaf with a trivial determinant. This is first-order class equals 0 here, and satisfying these bunch of homological conditions. And there is an integer C, which you can alternatively see either as the dimension of this particular cohomology here, or the second Chern class of this Instanton sheaf. This is called the charge of E, and again, the name is inspired by physics because in the initial situation for the instantons, the actual instantons on S4, these are precisely the topological charge of the Instanton connections, right? So this C is called the charge of the Instanton sheaf E. And these vanishing conditions you can check are equivalent to, it's all you need to show that such a torsion-free sheaf is the cohomology of a linear monad of this form, right? So again, you can find maps alpha and beta, which are matrices of homogeneous polynomials of degree 1 that compose to 0. Beta is going to be surjective. Alpha is going to be injective, but then injective, only genetically injective, so that the cohomology, the kernel of beta quotient out by the image of alpha, is allowed to be non-locally free, right? So this cohomology here is locally free if alpha is injective at every point. Otherwise, it's just a torsion free sheaf. And this notion of the Instanton sheaves generalized the so-called mathematical Instanton bundles, which were extensively studied in the literature, especially in the 80s and 90s. A bunch of papers by Okonek, Schneider, and Spindler. Actually, the first time where the terminology mathematical Instanton bundle appears, it's in the book by Okonek, Schneider, and Spindler. Later, Okonek and one of the S's, I'm not going to remember if it's Schneider or Spindler, wrote a paper on mathematical Instanton bundles on the odd dimensional projective spaces. There are a bunch of papers by Ottaviani, Rosa Maria, Mirohoich, and so on. So really, a lot of people study these bundles in the 80s and 90s, and but this generalization that I introduced in 2006 was not the final step, because the notion of these possibly non-locally free Instanton sheaves have been further generalized in various ways in the past 20 years. So before going to these further generalizations, let me summarize a little bit of the work done on rank 2 bundles on CP3. But it turns out that rank 2 Instanton bundles, rank 2 locally free Instanton sheaves on CP3, they are always mu stable with respect to this Mumford-Takemoto notion of stability. That's what the mu stands for, slope stable. In their moduli spaces, which are then well defined because all the sheaves are mu stable. For fixed charge, they have been extensively studied in the 80s and 1980s and 1990s. Here's a few landmark results. Laura Costa and Giorgio Ottaviani proved that IC is an affine variety. That was back in 2002. Actually, they prove a more general result, but it's not really so important right now. More recently, Alexander Tikhomirov showed that IC is irreducible. There are actually various intermediate results proved regarding irreducibility between the 30 years before Alexander's proof. There were various partial results leading towards irreducibility, and smoothness was established by myself and Misha Verbitsky in 2014. And actually, we proved this smoothness of the Instanton sheaves using the moduli space of framed Instanton bundles on CP3. Sorry, I should have written that here. So it's the moduli space of framed Instanton bundles of CP3 of any rank R rather than K, right? So of any rank R and charge C. These moduli of framed Instanton bundles can be constructed by a generalization of the ADHM construction, which is, basically the generalized ADHM equations. They look the same, is commutator of A and B plus ij equals 0, except that now A and B are not just matrices, but matrices whose entries are linear forms, right? They're polynomials of homogeneous polynomials of degree 1. So A, B, I, and J are now matrices of these linear polynomials, so that this equation here is now an equation involving. So the left-hand side of this equality is a matrix whose entries are quadratic polynomials. And then you want all of these quadratic polynomials to vanish. Right, so this is the adaptations. In the first case, when n is equal to 3, this is a sort of a complexification of the usual ADHM equations that give you the sheaves on CP2. And this is an example of a trisymplectic manifold. A trisymplectic manifold is sort of a complexification of a hyperkähler manifold, in which instead of having 3 Kähler forms, you have a triple of holomorphic symplectic forms. That's what the trisymplectic manifolds are, basically, quickly speaking. So this is sort of a summary of the progress on the study of the moduli space of especially rank 2 Instanton bundles on CP3. And another one direction that this study of Instanton bundles and complexes and monads led was also the notion of perverse instantons, which are objects in the derived category which are quasi-isomorphic to linear monads. So now this is still a complex. Alpha and beta are matrices of linear forms, of linear polynomials, but now the beta is allowed not to be surjective, right? So as a complex, this complex has no cohomology in this first entry, meaning that that's this condition here, age minus 1 is 0. So that's the same as saying that alpha is injective. The middle cohomology of this complex is a torsion-free sheaf, and the cohomology on this right position is a sheaf of codimension 2. So these are the this is actually, we were led to consider, so this notion first appears in a paper by Hauser and Lander, where actually they study the GIT problem applied to the space of monads. So if you take betas and alphas, you get all maps beta and alpha such that beta alpha equals to 0. This gives you an affine variety on which a group acts, the GL, VR, the GL of this vector space here. So we have a group acting on the space of all monads, giving you the the space of isomorphism classes of these linear moments. And so this is a GAT problem, right? So you have a group acting on an affine variety. This is a GAT problem. And it was studying this, what are the stable points for this GAT problem that Hauser and Langer discovered that you can also have stable points, GAT stable points corresponding to linear monads which do have a non-trivial cohomology in this side of the diagram, right? And these were called perverse instantons. As I was saying, this moduli space of these perverse instantons can also be constructed via the same generalized ADHM construction that I was mentioning about. The particular class of perverse instantons are the so-called rank 0 instantons, which is a perverse instanton so that the middle cohomology here is trivial, right? So it's a perverse instanton for which you take this R, this parameter R here, which is the rank of this H0 cohomology to be 0. This gives you a complex that its only non-trivial cohomology is in this position here, this position H1. And these are the so-called rank 0 instances. Another motivation to introduce this class of perverse instantons is that if you look at the derived dual of a non-locally free instanton sheaf, what you get is a perverse instanton, right? And this sorry, the H1 of this derived dual is a rank 0, is an example of a rank 0 instanton. So when you now think of these non-locally free instanton sheaves as elements in the derived category, as objects in the derived category, you have sort of naturally appearing these perverse instantons and these rank 0 instantons as well. So this is one direction of the generalization of the more abstract generalization of these rank 0 instantons, the instanton bundles. And also the non-locally free instanton sheaves can be regarded as some sort of a degeneration of the instanton bundles. So they sort of correspond to instantons on R4 that acquire some sort of singularities, right? So if you want to study instantons with singularities on S4, the right language to look at on the corresponding twistor space on CP3 is to consider the non-locally free instanton sheaves. Another direction of generalization of instanton sheaves was done by first by Kuznetsov and Faenzi. So there is this 2-year gap between the publication dates of these two papers, but actually this was work done by both authors more or less simultaneously and independently. In which these two authors, they introduced this notion of rank 2 instanton bundles on Fano threefolds in such a way that it generalizes the rank 2 instanton bundles on CP3, right? So generalizes the mathematical, what was traditionally called the mathematical instanton bundles on CP3. And the definition goes as follows. So if you take X to be a Fano threefold, you can write the index as 2k plus Rx, right? Rx is the remainder of the quotient of the index by 2. Remember, the index of a Fano threefold can only be 4 for P3, 3 for the quadric threefold, and 2 and 1, right? So the index is a number between 1 and 4, which means that this Qx, which is half of Ix, it's essentially 0 or 1 as well. 0, 1, or 2. And the remainder of the we fix to be either 0 or 1. Then, as Faenzi writes in his, Danieli writes in his paper, an instanton bundle on X will be a mu-stable rank 2 locally free sheaf on X, whose determinant is equal to the remainder. So the first Chern class is minus Rx, and then you have this cohomological vanishing. The H1 of E now twisted by minus QX is 0, right? So on the case of P3, when X is the three-dimensional projective space, QX is 2, and we get back the original definition of the mathematical instanton bundles. Except that on P3, every instanton bundle is automatically mu stable, but that's not going to be true in general for the funnel threefolds. So that's why the mu stability needs to be it's imposed here. And more recently, with a postdoc here, Gaia Komaski, we first also generalized this definition. We thought it was a good idea to consider non-locally free sheaves of arbitrary of arbitrary rank, not charge here, sorry, this is a typo. So non-locally free sheaves of arbitrary rank on funnel threefolds. So then we consider now an instanton sheaf to be a mu semi-stable torsion-free sheaf satisfying these two cohomological vanishings that again depend on the index, essentially on the index of the funnel threefold. And one of the theorems we proved in this preprint is that if E is a non-locally free if E is a non-locally free instanton sheaf, the word instanton here is missing. So if E is a non-locally free instanton sheaf of rank 2, then E double dual is a locally free instanton sheaf, and Q, which I'm defining as the sheaf double dual, right? So this star is the sheaf double dual, quotient by the original. So by the original sheaf, this will be a rank 0 instanton sheaf, right? And then rank 0 instanton sheaf here is a pure one-dimensional sheaf satisfying these vanishing conditions. So this is the notion that we introduce for the non-locally free instanton sheaves on X of arbitrary rank, including rank 0. Okay. If you ask me what is a perverse instanton in this context of a funnel threefold, I don't know yet. So it still requires a little bit of a creativity to define that. Now, this instanton condition, the cohomological vanishing, this cohomological vanishing here, together with the mu semi-stability, can be rephrased as this object, as this condition, right? So the instanton sheaf will actually be perpendicular to this line bundle inside the derived category, right? So we can sort of replace these vanishing conditions with this more categorical definition. So when you can think that an instanton object would be some object in the derived category that is perpendicular to this OXQX in the derived category of X. That's not quite what we want yet, because all the definition of instantons, they always come with some sort of fixing of the Chern classes and a stability condition, right? So in order to have a decent definition of instantons on derived categories, we should more or less know what is the good type of Chern characters to be fixed. How do we fix the Chern characters in this context? And also, what kind of stability condition should we impose so that the instanton objects do have a good, have a chance of having a moduli space. Lucky for us is that some funnel threefolds, namely the projective space, right? CP3, the quadric, the three-dimensional quadric, Q3, this Y5, which is the funnel of index 2 and degree 5, and also X12, the funnel of index 1 in the degree 12 or genus 12. It just so happens that the perpendicular of OQX is generated by a strong exceptional sequence. This strong exceptional sequence is made up of 3 vector bundles, chi-1, chi-0, and chi-1, in such a way that chi-1 is the dual of chi-1, and chi-0 is a rank 0, is an Instanton bundle. Actually, I wrote a rank 2 Instanton bundle here, but that's not quite true. I should just say that Y0, the chi-0 is a locally free Instanton sheaf of minimal possible charge. And this was something that Daniele Faenzi noticed in his paper back in 2014. And he showed that the rank 2 Instanton bundles, according to the definitions of the previous slide, can be represented as a cohomology of a monad of this form, right? So now, instead of having O-1, O, and O1, which is the case of P3, right? On P3, these bundles here, the chi-1 is O-1, chi-0 is O, so chi-1 is OP3 minus 1, chi-0 is OP3, and chi-1 is OP3-1. So instead of considering those linear monads, we now have to consider these other families of monads here involving these bundles chi-1, chi-0, and chi-1. Also, the other case that is easy to remember is the exceptional sequence for the Q3. For Q3, chi-1 is OQ is O-1, chi-1 is O1, but chi-0 is the spinor bundle. So you need to consider these monads with the spinor bundle here in the middle rather than the trivial bundle. And something that we haven't investigated yet is whether the notion of Instanton, this monadic representation also applies for the non-locally free Instanton sheaves that we just defined. So before going to the derived category, I should also mention that there is a very open definition of an Instanton bundle on any projective variety that generalizes the usual Instanton bundles on P3, the Instanton bundles on the Faenzi-Kuznetsov Instanton bundles on the Fano threefolds, also generalizes the higher dimensional cases of the Instanton bundles on CPN, which is the notion of these age Instanton bundles on a polarized projective variety. And this was worked out by a bunch of people from Torino, Francesco Malaspina, Vincenzo Antonelli, Ozan Genk, and maybe Casnati as well. I hope of not forgetting anybody, but all the group there from Torino made also a very nice generalization of all these notions of instantons for arbitrary varieties. And really, it's not clear. And they do also have monadic representations for their very general notion of instantons. Yeah, but it's not clear to me at least, whether the other parts that I'm going to talk about now also generalize. So in the past couple of years, what we realized, and this is this is something that was worked out in a recent paper with Anthony Machocha and Christian Martinez. So looking at CP3, right? So looking at the projective space, then we can consider these geometric Bridgeland stability conditions that were constructed by Emanuele together with Bayer, Macri and what's the other name? Well, Emanuele will help me later. So there's this, sorry?
Toda.
Toda, yes, Toda, sorry. I apologize for Toda. So that were this family of bridge instability conditions on funnel threefolds that are parameterized by three real numbers, alpha, beta, and these parameters, they are usually denoted by alpha, beta, and S. So I'm setting here the parameter beta to be 0. So a stability condition is a pair consisting of an abelian category, which is the heart of a T structure, right? So never mind too much what that is, but an abelian category and a central charge, a notion of stability in this abelian category. So here I'm fixing the parameter beta to be 0 and consider just the two other parameters, alpha and S, that have to be positive. We are fixing the Chern character to be minus, this vector minus R, 0, D, and 0, where again R and D are both positive integers, possibly 0. And then one can show that if you look at just this set, just this slice of the set of geometric stability conditions, we can show that there are no stable objects below this red line that I showed. So the red and the blue line are walls in these stability conditions. And below the red line, there are no stable objects, no semi-stable objects, actually. The modular space is empty. The shifted Instanton sheaf, so if E is an Instanton sheaf, and you shift this object by 1, so that's what I'm calling the shifted Instanton sheaves, and also the jewels, the derived jewels of these objects. They are actually semi-stable. They are all semi-stable above this red line. The stable ones are the locally free ones. So if E is an Instanton sheaf, if E is an Instanton bundle, arbitrary rank and charge. Yeah, sorry, no. If this is maybe just rank 2 here. So if E is an Instanton bundle of rank 2, they will be stable everywhere above the red line. Yeah, so maybe I should have fixed the R equals 2 here. So some of the things that I'm going to say is valid for every R, some only for R equals 0 or R equals 2. Let's fix this R equals 2 here so that I don't say anything wrong. So the Instanton sheaves will be semi-stable above the red line, and in between these two walls, between the red and the blue wall, an object of the form of a shifted sheaf, right? So if E is a sheaf, and then I just a shifted sheaf, then such an object is semi-stable between the blue and red lines if and only if E is an Instanton sheaf. Right. So these are some of the results we found recently, but a little bit to my surprise, this middle region may also contain further stuff, right? So in here I have an example of so this is an object of rank 0, right? So this is an object for the Chern character 0, 0, 3, 0. This OH and this extension here is an object with Chern class 0030. So this is not a perverse instanton. This is not an Instanton sheaf, not the jewel of an Instanton sheaf. This is not a rank 0 instanton. Nothing of the previous, the things that before I would call instantons, but it is stable between in this region between the red and the blue lines, and it is quasi-isomorphic to a linear complex, right? So it's something that by, by every other characteristic should be called, would be deserved to be called an instanton, but it wasn't detected by the previously, right? So that's what triggered us to consider a further generalization of this notion of instanton, which more or less goes as follows. And now back to the context of an arbitrary Fano threefold, we take these slides, this little piece of the stability manifold. So beta is going to be fixed to be a qx divided by 2. The qx is 0, 1, or 2, depending on the depending on x, right? So we take the beta 0 to be qx divided by 2, fix it. Alpha and s will be positive, satisfying this condition here. So this condition is the analog for the other threefolds of the blue line. Right? So when you take ix equals 4, right, you get precisely this blue line here. So we take this little region inside the stability manifold, fix these twisted Chern characters to be of that form, minus R0, D0. And then we can show that this region U here, below the blue line, will be divided into finitely many stability chambers. Actually, all of the walls here are these, are sort of bits of hyperbola parallel to this blue one. And they are nested, so they don't intersect each other in this bit of the plane. So you have a sort of a sequence of these parallel bits of hyperbola. And these are the chambers, that what the stability chambers look like in this case. And then an object in the derived category with this Chern character is going to be an instanton object if it's Bridgeland semi-stable for a stability condition in a particular chamber C. And then you can show that instanton objects are all perpendicular to this OQX. We sort of are defining it in such a way, right? So this definition here is so that an object is stable in this region here U if it will belong here to the perpendicular of OQX. And then we expect for the Fano threefolds that the instanton sheaves will be instanton objects also in this notion for some chamber, for at least one of these chambers. So this is the next frontier that I mentioned. Well, this is the current for frontier that of the instantons, the stuff that myself and Christian and also Daniele Faenzi we are thinking about. And perhaps the next frontier is, remember the big diagram that we had for the quaternionic projective spaces in the beginning of the talk? You can make similar diagrams for other quaternionic other quaternionic Kähler manifolds. And here's a family of quaternionic Kähler manifolds, the Grassmannian of two planes in a k+1 dimensional vector space. The twistor space of that is the projectivization of omega 1 of CP2K, which can be regarded as this flag of lines and one-dimensional and codimensional subspaces of a k+1 dimensional vector space. So these are these flags 1k, k+1. Okay. So this is the twistor space of the Grassmannian. The twistor map here is not a holomorphic map, right? That was quite clear from the get-go in the case of the quaternionic projective spaces, because the quaternionic projective spaces are not complex manifolds, but now the Grassmannians, these Grassmannians are both complex manifolds and quaternionic scalar, but the twistor space is always a complex manifold, but then the twistor map is not a complex manifold. So inside this, these twistors, you have the lower dimensional version of these twistor spaces, right? Which is the Grassmannian of two planes in a smaller, in a subspace of this k+1 dimensional space, and its twistor space, and then containing this this subvariety of the projectivization of omega-1 of CPK. You have a pencil of these other projectivizations here. So these manifolds here are playing the role of the even dimensional complex projective spaces. So this is this guy here would be the quaternionic blowup of the Grassmannians. And then there is a paper from back in the 90s, I guess, that work out what the so here on the Grassmannians, you can consider quaternionic instantons, quaternionic instanton connections, which you apply the Atiyah word correspondence, you get some holomorphic bundles on the flag manifold. And then there is a paper characterizing what are the instantons, what are the instanton bundles on this case. So the quaternionic instanton connections will give you holomorphic bundles on the flag that are cohomologies of this type of monad here. Right? Maybe a further study of instanton bundles on these flag manifolds could be quite interesting to develop in even these more derived categorical aspects of the theory I just mentioned. And there's perhaps even more interesting example. The third type of real eight-dimensional quaternionic Kähler manifold is this quotient of the G2, the Lie group G2, quotient out by SO4. So this is a quaternionic Kähler manifold whose twistor space is this generalized Grassmannian G2 mod P1. And as far as I know, nobody has worked out what are the instanton bundles on G2 mod P1, and it's still not clear to us also what is the quaternionic blowup of the G2 mod SO4, right? So this is perhaps the next frontier to be explored in this story, developing story of instanton bundles. So I leave with my happy birthday to Claudio. Live long and prosper. Thank you.
Thank you.
Okay, thank you, Marcus, so much. And is there any question for Marcus? Please, Claudio.
So, Marcus, thank you for this interesting and insightful talk. I have a very naive questions because I don't know very much about this, say, generalized instantons. Are I mean, in the case of a phanotrifles, these instantons sheaves, say semi-stable or stable, because this condition is not granted in this case. Well, the moduli spaces of these objects have been investigated yet, and because it should be natural to try to construct moduli spaces. Well, since you have a monadic description and so on, so should be
Yes.
quite similar to the classical case. Well, and
Yes.
hopefully also by means of representation of some quiver or so on. I don't know. Yeah.
So indeed, Daniele, in his 2014 paper, he does have some results about moduli spaces of instanton bundles on the rank 2 instanton bundles on the phanotrifolds. and he has existence problems in showing that the modular space of instantons has a component generically smooth of certain expected dimension, right? And he also looks at the definition of the modular space using these monads, right? As far as I know, the quiver story for these monads have not been worked out yet. So there's no such a thing as a ADHM equations for these more complicated monads. Very likely they will be very, I think there will be very complicated equations. I'm not sure what can you do once you have the equations, but then again, I don't really know what the equations are, right? But this is something that could be done. Maybe Daniele has been thinking about it. And also the other Torino group that worked on the generalized instantons on polarized varieties, they also have some results about the modular spaces of their age instantons. But none of the results approach this. You have no analog. We don't know if the modular space is irreducible, don't know if it's an affine variety, much less whether it's a smooth. Right, so it's
also this condition of trisymplectic is very interesting.
Yeah, there's no reasonable geometric structure on these modular spaces that have been studied yet, right? So the state of the art for the modular space of these instanton bundles is more or less what was for the instanton bundles on P3, say 30 years ago.
Thank you. Thank you.
Thanks.
Any other question for Marcus? Okay, so if not, let's thank Marcus again for this talk.
Thank you very much, everyone. It was really real pleasure to be here and give this presentation to Claudio. Thank you very much.
It's my pleasure, of course. Thank you, Marcus, again.
Thanks.